Hi everyone. So for this video, I will discuss the Newton-Raphson method for nonlinear system of equations. So given two nonlinear equations with two unknowns, we can equate this two functions or two equations into zero, and then at this form we can solve the system using an iteration of the Newton-Raphson method. So we can approximate the closest solution uh, using the first two terms of the Taylor series expansion. You know, so you have this f of x and y. Notice your first function is f of x and y, and then your second function is g of x and y. So equating this to zero and then finding the Taylor series approximation or the Taylor series truncation into two terms. We have this now. So the first term is just the function itself at the center. Okay. And then we have this what do you call this difference no from the center, and then the partial derivative of the function no, with respect to x. And plus we have the difference in y, so the other variable or the other unknown, and then the derivative of the function with respect to y. So why do we have three terms instead of two terms if this is the Taylor series expansion into no in two terms lang, di ba? So because we have two variables, and if we find that the total derivative of a function, if it has two independent variables, then it has to have two terms. No? So this is the first term and this is the second term of the Taylor series expansion. So, because again, the total derivative of the function is a sum of the two partial derivative or two partial derivatives of the two independent variables. Okay, so remember that. So with this knowledge, so we can also do that for the other function. We can create an iteration function that will help us solve for the approximation of x and y. And manipulating this, so we can transfer this f of xn and yn and g of xn and yn to the other side, so it will become negative. And then transforming that into its matrix form, you know. So this is the negative sign that we have, you know, and then we can transform actually this function or this system of equations into its matrix form. No? So this does look similar to what we did or what we are doing in linear algebra, wherein this, no, this is the first unknown, no, and as you can imagine, this is the second unknown, and you can imagine the derivatives here. The derivatives here are the coefficient matrix. So if we simplify this, we have this in matrix form, in this form. So what we have here, no? So this first matrix is actually called the Jacobian matrix, no? And we can call this the delta Z matrix for now. And then we have this H matrix, no? So we have an operation or a matrix operation of the Jacobian times the Z matrix, and then that is equal to somewhat a constant coefficient, the H. No, actually they should be negative. So let's describe the following matrices. No? So the first matrix is the Jacobian. No? So the Jacobian matrix is just a collection of the derivatives of the function, or to be exact, the partial derivatives of the function, depending on which unknown, no, are we talking about. No? So let's say we have a 2 by 2 nonlinear equation. So for the first row, we are trying to find the partial derivative of the function f with respect to x and with respect to y. So yun yun, no? So the first row is f only, and then we have here the partial derivative with respect to f and the partial derivative with respect to y. So for the second row, we have the g function, and same thing, no? So we have the partial derivative with respect to x and the partial derivative with respect to y of this g function. So again, the Jacobian matrix is just a type of matrix, or a type of matrix wherein this is just the collection of the partial derivatives of the functions depending on the independent variables available. So for the delta z, we can simplify this as delta xn, since this is the difference between the center, actually this is the center, and another point in the function. No? So we can create an iteration function using this difference. For later, we will discuss this. And then the h here, which is just the two functions, no? That's it. No, they're just the functions in the right hand side. Each function. Now, if we want to expand this iteration function, no? So we are interested in solving the system of linear equations, but we can create an iteration function using this given this matrices. So if let's say we want to solve, no, if you can recall, we have a system of linear equation Ex is equal to B. To be able to solve this system of linear equation, if you can recall, we can find the inverse of the matrix. So we have the inverse of the matrix times B is equal to the solution X. So this is what we do in linear algebra. We can find the inverse of the coefficient matrix and multiply that by the constant matrix B. So we can do the same with the Jacobian. We can find the inverse of the Jacobian so that we can solve for the delta z. So we have the inverse of the Jacobian and then multiplied by negative h. Okay, so this is the solution to your system of equations, no? And just expanding into this, no? So we have this Jacobian. How do we find the inverse of this Jacobian? So the Jacobian, as we recall, is just a collection of the partial derivatives of the function. So let's say x and y, function f, okay, and then partial derivative of the function g with respect to x and with respect to y. Now, if we want to find the inverse of this function, we find the inverse. If you can recall, now we have the formula. If you have a given A that has or a 2x2 matrix A, let's say with entry A, B, C, and D, then therefore the inverse of its matrix, inverse of its matrix, so this will be equal to what now? So we have 1 over AD, we have AD minus BC multiplied by D, and then A here, and then negative B and negative C. So this is how we solve. No, this is just a shortcut method for finding the inverse of a 2x2 matrix. For 3x3 matrices, we don't have an example anymore, but you can recall also if you want to find the solution of 3 unknowns and 3 equations that is a nonlinear system. So again, now how do we find the inverse of this Jacobian? So to find the inverse of this Jacobian, so the inverse of the Jacobian will be equal to, so based on this, we have AD, so this would be A and D, right? So we have 1 over the partial derivative of f with respect to x times the partial derivative of g with respect to y, and then minus the partial derivative of g with respect to x, and then multiplied by the partial derivative of f with respect to y. Okay, so we're done with the first portion, and then for the matrix, we have D here, so this will be just the partial derivative of G with respect to Y, and then the partial derivative of, the negative partial derivative of F with respect to Y, and then the negative derivative, or the partial derivative of G with respect to X, or we can call this del, no? Del G, so del F over del Y. So partial derivatives, we can call them the del, no, instead of del B. So that will be the inverse of your matrix. Now, expanding this, no, so if this is the Jacobian, or the inverse of the Jacobian, then the solution of that is just multiplying this no? This two matrices. So we have negative h and then this inverse. So the delta z will be equal to, we have 1 over this, okay, we have del g over del y, and then minus, we have del g over del x, del f over del y. And then again this g and then del y, negative del f over del y, del g over del x, something is negative, and then del f over del x. So multiplied by the h, no? So the negative of the h. So we have here, actually the negative can be multiplied to the scalar, no? So this can be multiplied by the negative sign. So if we multiply this by the negative sign, actually we can distribute this negative sign to each of this. So we can swap the signs effectively of our denominator here. This will be positive, this will be negative, no? And then the h will be the f, no, the f function and the g function. So the delta z can be also equated as we have xn plus 1 minus x sub n, and then y sub n plus 1 minus y sub n. Okay, and then creating an iteration function for this. So we have the first row here, and then the multiplication of the first row and the first column of this two matrices, and we will arrive at the same at this equation. Ano? So simplifying that, we can get these two equations for helping us solve the system of linear equation using this Newton-Raphson method. So I guess you can read this algorithm in the PDF, but I will just get into the example, to make things easier and more concise. So let's say we have a given, or we have a given system of nonlinear equations. Yeah. And then we have a given, or we have the given initial values. So the initial guess says, how do we now solve this using the Newton-Raphson method? Okay, so the first thing we should do, so the first thing that I discussed is that we need to equate this two equations into 0. So we can manipulate this first equation. So 3x plus 8y, this should be negative 9 is equal to 0. So transposing this negative 9 and this positive 9 to the other side. And then also for the second equation, we have x squared plus y squared minus 16 is equal to 0. So basically, this is your, you can recall we have the f of xy is equal to 0 and g of xy is equal to 0. So sometimes we can just refer to this as the function f and the function g. So we will call this the function f and the function g. And then what's next? We can solve for the Jacobian. So the Jacobian is next. So to find the Jacobian of your system of nonlinear equations, we want to find the partial derivative of f, no, with respect to x and y, no. And then for the second equation, so this is g, the partial derivative of g with respect to x and with respect to y. So therefore, the Jacobian matrix, no, can be equal to, will be equal to, or actually I'll just write here the values of the Jacobian elements, no. So the partial derivative of f with respect to x. So if this is your f, the partial derivative of this with respect to x. So what does this mean? So if we are trying to find the partial derivative of a given function or a multivariable function, then this will be the variable, no? And then everything else, or every other variable will be treated as a constant. So the y here will be treated as a constant. So therefore, we're just trying to find the derivative of 3x. And then this will be, the derivative of this will be 0. So we have here 3 for the partial derivative of f with respect to x. And then the partial derivative of f with respect to y. So again, we treat the y as the variable and everything else is constant. So the derivative of 3x is 0. Derivative of 8y is 8. Derivative of negative 9 is 0. And then the partial derivative of g with respect to x, that is, okay, so we have this function, actually this one only, you know. So this function, we have the partial derivative of g with respect to x. So we treat this as constant, so the derivative of this is 0. So the derivative of x squared is 2x. And then for the partial derivative of g with respect to y, that is what? No? So we treat x as constant. So the derivative of x squared is 0. Derivative of this is 0. So what is the derivative of y squared? So this will be just 2y. 2y. Yeah. So what's next? We have the formula, no? So I already written down the formula just to save a little bit of time, no? So for the iteration function, we want to set up the iteration function that we will use for your approximation. So for the x term, so we have x here. So this is equal to x, no? So actually this will be just the k, and this will be the k minus 1. And then we have plus, okay? We have plus, what is the g? So the g here is this, no? So this one is the g. So we have x squared plus y squared minus 16 multiplied by del f over del y. So this will be just multiplied by 8 minus f. So f here is this. So f is 3x plus 8y minus 9. And then multiplied by del g. So del g over del y. So we have 2y. Yeah. And then all over. So we have del f over del x. So we have 3. And then del g over del y. So we have 2y. And then minus, we have del g over del x. We have 2x. Del f over del y, which is 8. Okay, so we will utilize the previous values of this. I'll just write here x k minus 1, k minus 1, k minus 1. And then for the y variable, so the iteration function, so the present value of y will be the previous value of y plus this, no? So we have this formula, so we have f. So what is f here? We have 3x plus 8y minus 9. And then del g over del x, we have 2x here. So this is 2x, ano? 2x. Okay, 2x. And then minus g, so g is x squared plus y squared minus 16. And then what's next? So del f over del x. Del f over del x. Where is this? So we have 3. So 3. And then over, so the same, both of the iteration function has the same denominator. So we can just write this down again, no? So we have 3 times 2y and 2x times 8. Okay, so what strategy should we use here, no? Is that similar to the Gauss-Jacobi, wherein we will just utilize the previous iterations, or the latest one, similar to the Seidel method? So for this, it actually depends on us, no? To what should we use. Kasi in fixed point iteration, we have a similar strategy with Gauss-Seidel, wherein the most available is used, no? But in here, no, actually the textbook says, doesn't explicitly say if we should use the Jacobi or the Seidel, although the example there in the textbook, the author used the Jacobian strategy. So basically, every iterations of the next variable will still be the previous. So k minus 1 pa rin lahat. So Jacobian or the Jacobi method is similar to the Newton-Raphson, although we can use the Seidel strategy. Okay, so we already set up our equations. So let me just label this, no? So the a here will be your x, and the b here will be the y, no? So let's utilize our calculators, and let's set this up, no? yung ating iteration table. So for iterations, okay, so the iterations here, we have the x and we have the y. So initial iterations, we have the initial guesses, we have 4.1 and negative 0.2. So let's set up the iteration function. So we have alpha a for the first equation plus we have a squared plus b squared minus 16 and times 8 minus we have 3a plus 8b minus 9 and then we have 2y. Okay, and then we have this will be just 6y, no? So I'll just write here 6e minus, so 2 times 8 is 16, so 16a. Okay, and then calc. So let's try this. We have 4.1 as the initial guess and negative 0.3. So the initial iteration for x is 3.9852. Okay, and then for the next one, so we will use a new iteration function. So for y, we have alpha b plus we have 3 alpha x plus sorry, not x but a, no, sorry, a plus 8 alpha b and then minus 9 and then 2x, so 2 alpha a minus a squared plus b squared minus 16 times 2. And then we have 6y, so 6b minus 16a. So calc and then substitute the previous. No? So we will not utilize the most recent value of x. So negative 0.3 and 4.1 only. So we have negative 0.3694. And then for the second iteration, we can just utilize the previous one. So the previous formula is this, and then we can just update the values of x and y. So this will be 3.9852 for x, and then negative 0.3694. So 3.9830, 3.9830, and then for y, so another one. Okay, the same thing now. So it is much easier to use the Jacobian strategy, you know, so negative. It is much faster since you don't need to change it every row. It is the same values. And then for the next iteration, so back again for A, so we have 3.9830 for the previous, and then negative 0.3686. So we have already we have a repetition, so 3.9830, and then for last, probably this will not repeat, or this will repeat already. Okay, so we have a repetition, so this will be the accuracy will be 0%, no? Sorry, the accuracy, but the relative error will be the same. So as we can see now, this has the same decimal places. So therefore, your approximate value of x is equal to 3.9830, and the approximate value of y is negative 0.3686. So this will be your answer for the solution using the Newton-Raphson method up to 4 decimal places. Okay, so that's it, no? So we will only limit, at least at this course, the solution for the system of nonlinear equation into two by two equations and unknowns. So we can generalize this. Anyways, we can also solve 3 equations, 3 unknowns, 4 equations, 4 unknowns, 5 equations, 5 unknowns. But you can see the gravity of the calculation. No? So you want to find the Jacobian matrix of the function and also the inverse of your Jacobian. So the general case of this is that if let's say we have n number of equations and n number of unknowns, then the Jacobian will be this. No? So we have an n by n Jacobian. So let's say we have 10 equations, 10 unknowns. We have 10 by 10, a 10 by 10 Jacobian matrix. And we have to find the derivative of that. No? So the partial derivative with respect to the column variable. So you will operate, or you will want to find the call this, the partial derivative of the functions 100 times kasi 10 by 10. No? And then that is not yet the end. You have to also find the inverse of the Jacobian. So finding the inverse of the Jacobian of a 10 by 10 matrix can be troublesome then as well. But there are different other ways of solving this. Even by not using the inverse, there are different methods for approximation of the inverse of the Jacobian. Okay, so that will be all for this video. So good luck in class, and I hope you can answer the exercise. Thank you, guys.